Good morning, everyone, and welcome to today's webinar, Innovative Services to Monitor the Spatial Distribution of Human Activities. I am Sara Garavelli, and I'm the Outreach Manager of the Horizon 2020 BlueBRIDGE project, which has organized this webinar. BlueBRIDGE has developed a set of innovative data services, what we call Virtual Research Environments, or VREs, and the purpose of this webinar is to describe two VREs that have been developed in the project. The first one is specialized in recognizing offshore fish farming in Greece, while the second one is specialized in identifying coastal aquaculture ponds in Indonesia. The duration of the webinar is around 1 hour. We will have a 40 minutes presentation from our speaker, and then we will reserve the final 20 minutes to answer to your questions. You can pose your questions through the question button of GoToWebinar. I'm pleased now to introduce the speaker of today, Nicolas Loegepé from CLS, the French satellite service provider. Nicolas is currently a research engineer in the radar application division of CLS. He has worked with CLS since 2010, and before he was with the Earth Observation Research Center of the Japan Aerospace Exploration Agency in Tokyo. His research interests include spaceborne remote sensing applied to maritime security and to environmental and natural resource management. Thanks a lot, Nicola, for having accepted our invitation, and now the floor is yours.
Okay, thank you, Sarah. Good morning, all, and thank you for attending this webinar. So, my name is Nicolas Loegepé. I'm with CLS, which stands for Collect Localization Satellites. At this stage, I'd like to acknowledge all my co-workers and partners in these activities. So people at CLS that you can see here, but also people at FAO, Emmanuel Blondel and Anton Dellenbroek, and all people from CNR in Italy. So first of all, I'd like to introduce in few words CLS, which is a private company. CLS has a workforce of about 700 people all over the world. We have 26 sites around the world. So the main office is based in Toulouse, which is southwestern part of France, while I'm based in Brest, which is on the Brittany part of France on the western coast. So CLS is active actually in 6 strategic sectors: environmental monitoring, fisheries, maritime surveillance, energy and mining, fleet management, and space and ground segments. So CLS provides satellite-based services for geopositioning and environmental data collection. So data from about 80,000 transmitters are processed each month. It can be drifting buoys, animals, fishing, or merchant ships. We have also some services to observe ocean and inland waters. We use more than 20 spaceborne instruments to monitor ocean daily. We monitor also terrestrial and maritime activities. So we process 10,000 radar images per year. And actually, this webinar focuses on aquaculture mapping with Earth observation imaging. So we are at the intersection of 4 sectors addressed by CLS. So fisheries, environmental surveillance, maritime surveillance, and space. So as it was mentioned by Sarah, this activity is part of the BlueBRIDGE project. It is funded by the European Commission under the Horizon 2020 programs. So it's aimed at providing services linked to aquaculture and fisheries. So the core of BlueBRIDGE is actually to build what is called VRE, so virtual research environments, for supporting multidisciplinary activities by exploiting capabilities of common infrastructure. So this common infrastructure here is called D4Science. So after this webinar, and if you join the VRE, you will get access to the slide and you will be able to learn more about what is VRE and what is BlueBRIDGE. So you will get access to the link provided here. And so the whole idea for you is to remember that a VRE is an online system, so it is on the web, that includes services, data, and computational facilities. So I guess all of you are quite well aware about the challenges of aquaculture in the years to come. So to sum up in few words, so we have to feed an increasing number of people on this planet Earth. So fish is a primary source of animal protein for many people in the world. But meanwhile, the ocean biodiversity is in danger due to many aspects. Overfishing, illegal fishing, it can be also pollution from maritime transportation, and many other ocean activities. There is also an increasing concern for environmental protections, and in addition, maritime spatial planning become very important to manage altogether all the uses of maritime space. So it includes also maritime renewable energy. So having that in mind, we would like here to have and to generate geospatial aquaculture products. So this is the final aim of this theory. So the idea was to build what we call here AAPS, or Aquaculture Atlas Production Systems. So it takes Earth observation images as input and generates aquaculture geospatial product. So aim is to explore the capabilities of the European Copernicus program with both Sentinel-1, which is a radar sensor, and Sentinel-2, which is an optical sensor. So we produce this geospatial product, which will be stored in the D4 Science infrastructure and will be available for expert use for review. And then it will be made available to public online. There will be 3 use cases. The first 2 with fish farm detection, so in Greece and Malta, and the third one with coastal pond monitoring in Indonesia. So here is the general architecture and workflow of the proposed system. So on the top right corner, you have the input data, so Copernicus imagery. On the bottom right, you have the different users. So at this stage, we define 2 types of user: a super user with the guy wearing the necktie here, and the normal user. So the normal user can actually just browse the results, while the super user can interact actually with the data and modify some features which are stored into the infrastructure. On the top left here, you have the various software which is used to produce actually the geospatial product from Earth observation imagery. We'll come back to this part later. And then, as I mentioned, we will use a D4 Science infrastructure that will host all the generated data, but also the web interfaces, the services for user identification, and all data publication and modification process. So this webinar will be organized as follows. So we'll first speak about the data access and archiving systems. Then I will speak about the data production. How can we generate the geospatial aquaculture product? And then we will speak about data visualization and editing tools online. So let's start with the first part, which concerns the data projections. No, sorry, the data archiving and access systems. So as I said, we use various kind of satellite imagery as input or AAPS. So the first source of data is the Sentinel-1, which is a radar sensor. So it's a so-called synthetic aperture radar, which is high resolution radar sensor. So the resolution of this kind of sensor is about, let's say, 10 meters to simplify the programs. And then we have the Sentinel-2 mission, which is also a Copernicus mission. It was launched in 2015 for the first one. And so this is an optical sensor, and the resolution is about also 10 meters. For the Greece and Malta study case, we will use very high resolution imagery coming from IT companies like Microsoft or Google Earth. And the main advantage is, of course, the high resolution data. So here is about below 50 centimeters. So the resolution is very good. But the main disadvantage is that you have no control on data processes, data quality, or data revisit. So this is the main drawback of this kind of data source. So we'll come back to this source of data later on at the end of the webinar. And the fourth source of data which has not been explored actually within the project is the Sentinel-3, which is a mission, a Copernicus mission, which is dedicated to the ocean monitoring, and that could be used also for water quality, for example. So actually, all the inputs of this IPS goes through the CLS Maestro EODA systems, where actually act as a kind of scheduler for images. So it takes Earth observation data as input, and then launch the various required processes to prepare the data, produce GeoTIFF from native Sentinel-1 or Sentinel-2 formats, and launch a specific algorithm via WPS, or Web Processing Service, to generate all the aquaculture products. And then actually this system also will be used to broadcast the images via WMS processes. So once all the various source of data has been formatted, we start the production of the geospatial aquaculture products. So we start the second part of this webinar. So for the Indonesia, and especially Sulawesi, here is the challenge. We would like to detect actually aquaculture coastal ponds, knowing that optical sensors actually often fail because you have clouds, permanent smog, and you cannot have access to good images. And from a sensor point of view, it's very, very difficult to discriminate flooded rice paddy field and coastal agricultural ponds, because from a sensor point of view, it's just water surfaces. So this is why the idea is to actually exploit the revisit capabilities of the radar, because radar penetrates the clouds, it works day and night, whatever the meteorological conditions. And with Sentinel-1, you can also track the rice growth cycles through the seasons. So the idea will be to combine the two, so Sentinel-1 and Sentinel-2, so that we can expect to discriminate coastal ponds from rice paddy field, from actually all the other type of land use and lawn cover types in this particular region of the world. So as for Sentinel-2 and the detection of permanent water body, we use the NDWI, which is a normalized difference water index, which is the normalized ratio of the green channel and the near-infrared channel. So here the idea is to stack all the available images to remove false alarms due to, for example, cloud cover, and finally use a threshold on this index. We did some trial actually to remove river from our detection, but this could be eventually done with ancillary data. But unfortunately, we could not find any good database with sufficient quality. So river and coastal point might be ambiguous in some area. So this is a kind of perspective to these activities. So as an example, this is an example of NDWI index in South Sulawesi. And here you can see the ocean on the left part. In the middle, you have a coastal pond, and on the right, you have other type of vegetation. So using this kind of index, you can clearly see the different land use and land cover type in one specific region. As I said, we use also Sentinel-1. Sentinel-1 will be used actually to track the change of radar signals through the time, while stacking all Sentinel-1 over 2 or 3 years. But to do that, we have to define a ground truth database, and we did that with Google Car. And thanks to the picture of Google Cars, we were able to identify actually the different land use and land cover types from the pictures themselves. Then we built an algorithm based on machine learning techniques so that we could classify the radar signal and time series of radar signals, so that we can discriminate brackish ponds and rice paddy fields via the rice growth cycle that we can monitor with the radar sensors. So finally, at the end, we fused the detection coming from Sentinel-1 and Sentinel-2, and we obtained the final product. So this is the main idea for the Indonesian study cases. So this is how it works. For the study case in Greece or Malta, the challenge is very, very different. Here, actually, we would like to detect and characterize the fish farms in coastal area. So below here, you can see some overview of the typology of fish farm that you can see in Greece. So they are generally made with flexible fish cages, with size actually range from 10 to, let's say, 50 meters. They are made with plastic materials, so either with square shape here that you can see, or circular. So clearly, with this kind of feature, you cannot detect them with Copernicus decametric sensors. We try to do that, but of course, due to resolution aspect, it's you can barely see them on Copernicus images. That is why we actually moved towards the use of very high resolution images provided by Google Earth or Bing. So as you can see here, with this source of data, the delineation of all fish farm could be possible. But if you had to do this manually with a full delineation by hand, it will be a real burden. For example, if you consider Greece, you expect to have more than 200 fish farms, and for each farms you have dozens and dozens fish cages. So if you had to delineate all these fish cages by hand, it would have been a nightmare. So this is why in our approach, we implemented an automatic algorithm actually to delineate and detect all these cages automatically. And this algorithm is actually included into a dedicated GIS software. So this software is called Acuity. This is made by CLS. So its specificity compared to other standard GIS software like QGIS or ArcGIS is that it is very simple, intuitive, and dedicatedly tuned for the needs of the sectors. And it is directly connected to the WPS of Maestro, so that the ingestion of Earth observation data is very easy. You can add also ancillary information such as bathymetry, meteorological or ocean variables. You can add wind speed, current, sea surface temperature. Screen sharing, okay. I hope that you can still see my screen, sorry. So as you will see in the video demonstration in a few seconds, there are 4 main steps to process with the fish farm detections. First of all, you select the region of interest. Then you run the dedicated algorithm to detect automatically the fish farms. And then you can eventually edit manually the contours of the fish farms and the fish cages. And then you can fill some attribute to each fish farms. So then we will move to a video that I prepared for you showing the Acuity toolbox. So I hope it will work. Okay. So here you see the Acuity software. So on the left you have you can browse to a particular location on the image. Oh, sorry, it's the demonstration effect. The video cannot run. Okay. I see that there is a problem of connection. I'm very sorry about that. Hopefully it will come back here. Yeah, so here you see the people actually delineate the area, the algorithm was run, and then the algorithm automatically detected all the fish cages in one specific area. Then the user actually can edit some features, and then at the end you can click to another area, which is done here. The user can select again the region of interest here. Then the user actually will run the algorithm, which is done just now, and then the result just appears. The algorithm actually is very fast. Then the user can actually modify the delineation, add some rounded fish cages or square fish cages, and then again the user can edit some attributes on the left. So this is how it works. I will move to the slides again. Hopefully it will work. Okay. here we come back to the slides. So the last part of the VRE is about data editing and visualization. So as a reminder, this part is fully integrated into the D4Science infrastructure, meaning that the data is available for any user. All the developments are actually hosted by the infrastructure, hosted at Siena in Italy. And so here, as already mentioned, there are two levels of user. So the super user here, who can actually edit the attributes of the generated geospatial data, and the simple user who can only visualize the product. So the requirements for this platform were to have one platform to visualize the geospatial product, along with Earth observation imagery used to produce them. The possibility for thematic expert user to edit and modify online some attributes. And three, to ease the validation and publication of all these validated products into a standard format and with a portal. For instance, here we'll use a GeoNetwork. To do that, we had to use the following features. So we use a React framework to develop the web app. So we aim here at to get a dynamic and fluid navigation on the website. So the handling of user profile is actually integrated via specific services hosted by D4Science infrastructure. So we work with WFS to display the layers via a GeoServer hosted by the infrastructure, for instance. And the update of the layer is done via WFS-T. So T stands for transactional. So and all the Earth observation imagery are actually broadcasted by WMS processes from IODA and Maestro portal. So when you will connect to the VRE, you will get access to 3 use cases. So Greece, Malta, and South Sulawesi. So the first 2 are based on the same functionality and deal with fish cages. And the third one that you can see on the bottom right here, so concerns South Sulawesi is for coastal land use and land cover classification. So for the fish farms, you will be able to browse over each fish farms and get the attributes of one specific fish farms. The super user will have the possibility to have a panel on the right to be open for each fish farms, and then the super user actually may be able to edit the different attributes and edit all the metadata that are here. And then the super user may be able to see all the validated and all the modified fish cages. Once validated, actually the publication of OJC compliant geospatial vectorial data actually is done via the GeoNetwork portal. So for those who will have normal profile and who are not super user, you will have access to this type of web pages by clicking on the link provided for each field of each validated forms. So for the Indonesian study case, you will be able to see all the generated products. So we use, as I said, Sentinel-1 and Sentinel-2. So for the coastal pond detection versus rice paddy field, which has been generated over the period 2014-2017. We did also the same classification work with Landsat 5, so just using optical imagery. So here we could just detect coastal ponds, so over the period 94-97. So here actually you can compare the two. During 20 years of time lag, you can see the different change of the coastal use, which is you can see on the 2 figures on the bottom. You can also display radar images, which is also very important here, is to show how can it be used and how you can highlight the different features detected. So now it's time to move to the conclusion and perspectives of these activities. First of all, we'd like to mention all the benefits to work within a VRE. So actually, all the storage of generated product is available within a single platform. So it's opened the possibility to integrate this data with other data sets and actually interact with other communities. It can concern the environment, it can concern society aspect, economy, and so on. So really you can use that for many other purposes. So we have here a standardized attribute compliant with FAO specification and also OGC standards. And as a reminder, this study has been funded by the European Commission. So here we have now a portal to showcase the use of Copernicus, Sentinel-1 and Sentinel-2 satellite imagery for this sector of aquaculture. So we expect this VRE to have some positive impact for national and international organizations. They will be able to list and follow the evolution of aquaculture fish farming through the time. Here we provide two use cases, Malta and Greece, but this could be easily replicated to other areas with a full inventory of the evolution through times. With the study case in Indonesia, it could be extended to other areas in the world as well, and regional assessment of coastal wetland use can be done, and also you can assess the temporal evolution of this use through the time. The next step would be to get some user feedback from end user. Also within BlueBRIDGE project and with other partners like FAO, SNL, we will have to agree on a sustainable model for this VRE. Here, as it was research and only study cases, we use Microsoft Bing imagery, but if we want to scale up to some other area and other periods, this source of data may not be suitable because of licensing issue and data constraint. In addition, we should work on the mechanism to handle inventory requests and updates for other countries or periods. And as Copernicus imagery provide a continuous flows of data and terabytes of data, how can we work toward an open, free, and systematic approach using this type of data? This is an open question. And there is also a need to set up partnership with expert institute or local expertise. So that we can have better ground truthing, we can have validation, we can have a better intercomparison with other data sets. We could also integrate the generated product into other systems. So this is some perspectives. There are also some, let's say, mid-term or long-term perspectives. One of them could be the possibility to implement, for example, an unsupervised system screening for fish farms for all the coastline for all the countries in the world. So in that case, we'll have to deal with other techniques to level some ambiguities using machine learning and probably deep learning techniques. Also, we could implement real-time application. This is a possibility. And especially, we could demonstrate the feasibility to have near real-time pollution detection from aquaculture using Copernicus 1, Sentinel-1 or Sentinel-2 data. We could also support the industries with water quality monitoring. So to perform this, we could use Copernicus Sentinel-2 or Copernicus Sentinel-3 missions that could be used. Our objective is here to actually fill the gap between the different communities, remote sensing and the aquaculture industries. So finally, I'd like to say that the VRE is available for you. So you are welcome to sign up today and join us in this adventure. So please go to this website and sign up today. So I guess this is the end of this presentation. If you have any question, please do not hesitate. Thank you.
Thank you very much, Nicola, for the very clear and inspiring presentation. So now, as you said, we leave the floor to the questions. So please, I am asking our participants to post their question in the question box. We do have already a couple of questions. The first one is, how long does it take to build a new atlas for a new country?
Your question concerns fish farm detection or coastal ponds? It's at least for fish farms, it really depends on the size of the country. To give you an example, for Malta, this is let's say few minutes to generate all the fish farms, because in Malta there are not so many fish farms. For Greece, it's manually, if you don't have these capabilities that we developed, it would have been probably weeks to perform, because you have, as I said, you have 200 fish farms in Greece, and for each farm you have many fish cages. And with the algorithm, it takes no longer than 1 or 2 days to do it using a standard work day. For the other area, which is Indonesia, to reply to this question is a bit more complex, because it's really depend on the typology of land use, land cover that you have. So the algorithm actually for now is a supervised algorithm, meaning that we have to train the algorithm to classify the different land use, land cover types. And this training step might be quite long. And here you have to go through, let's say, a research activities to develop maybe a refined algorithm. So I cannot clearly reply to this question for the Indonesian study case, but at least for the fish farm detection, it can be very fast, and even for a country like Greece, it was very, very fast to process.
Okay. And then there is another question asking what were the main challenges in building the Aquaculture Atlas VRE?
Well, the challenge is really to fill the gap in between the different communities, because basically here we try to bridge the aquaculture needs to the Earth observation imagery, and you have to go through this VRE, which is IT stuff. So basically, it's a combination of 3 aspects. So you have the thematic information, which is aquaculture. You have Earth observation imagery, which is also quite complex to handle, because you have to go through terabytes of imagery, and you have these IT processes and this VRE stuff. So bringing them together was actually quite a challenge.
Okay. Then we have a more technical question. Can you train an algorithm to run, for example, every month in Indonesia?
To what? Sorry, I cannot.
Can you train an algorithm to run, for example, every month in Indonesia?
Yeah, that could be done. Actually, the number of acquisition, especially for Sentinel-1 over this area, is very good. So you have many images. I don't know how many images per month, but you have some images of Sentinel-1 coming up every month. So these images can be used to rerun the algorithm. So once the algorithm has been trained, it can be rerun with the new images coming up every month. So I will say that we don't have to retrain the algorithm if we focus on the same area. But the algorithm can be updated. I mean, the result could be updated every month, every 6 months, or every year easily.
Okay. And how will the system assess water quality in shrimp farms?
So for now, the water quality has not been integrated. So as I said, this is a perspective to this task. Water quality could be provided by 2 sensors. So the first one is Sentinel-3, which is really dedicated to this measurement, and you have also Sentinel-2, which is high resolution, but in terms of spectral bands, I would say it's less adapted than Sentinel-3. But anyway, so having this water quality index coming up to the VRE is possible, and but up to now we have not done this within the BlueBRIDGE project, but this is possible.
Okay, now we have a question on the data sources. Does the Sentinel-3 data give enough information, or are other information sources needed too?
To get which kind of information? Water quality?
I don't know. This is not specified in the question, so I ask the person to specify. Water quality.
So no, water quality can be directly retrieved from this kind of sensor with no anterior data provided. So with using multispectral information coming from this sensor, you can actually extract the water quality, water turbidity, sediments, and so on. So you don't need any other ancillary information. But for sure, for Sentinel-3, the resolution is quite coarse. It's about 500 meters. So then you may not have high resolution information, but still at coarser scale, then it might be useful.
Okay. Then we have a question more on the impact of your work. So have you had any feedback from aquaculture management or governance bodies in Greece or Indonesia?
No, for now, I mean, this is the user feedback has not been collected, so the VRE is just open from a few months now, and we did not collect any user feedback now, but with FAO, which is our partner on this activity, we expect to have many user feedback from national and international organizations, either in Indonesia and Greece. Yeah, but now we don't have.
Okay, then we have a more technical question going back to the water quality. So because there are two different areas, tropical and subtropical, what is the atmospheric correction method to retrieve the water quality?
Well, for this question, sorry, I cannot reply precisely. I'm not personally an expert on water quality index and Sentinel-3 sensor, so I'm sorry, I cannot reply to this specific question.
Okay, I guess that this person can send us an email, and maybe you can forward it to your colleagues. So, okay, then we have another question. Would you be interested in a service we are offering called Sentinel-1 on demand?
What's that mean?
I think it says on-demand downloading and processing of Sentinel-1 data with user-defined processing graphs, scalable heavyweight high-performance VMS, web interface for job development.
Yeah, for sure. Well, this is something that we could do in fine within BlueBRIDGE, is to have like on-demand services, but that was not the scope of the project. But for sure, this is a perspective to this sector, is to have like a direct connection in between Sentinel imagery and product generated on the fly.
Okay. And then we have a last question asking if you can recap what are your plans for the future for these VREs.
So the plan clearly is so now maybe the main plan is maybe to have an unsupervised screening for coastline. I think this is a very interesting perspective. Is to scale up the process here, as you can see in the video, the analyst has to supervise the algorithm and say, here you should be able to detect fish cages. But one perspective could be to have an unsupervised algorithm, so screening all the coastline for one specific country and do it automatically without any human interaction. And this will provide very useful information for the community, I guess, is to have all the information which is made and processed consistently through all the countries. For sure, it will need to have a more refined algorithms, and an algorithm which is able to also to remove all the false alarms and work with all the typology of fish cages, but this is, I guess, a very interesting perspective to this activity.
Yeah, it is. We have another question in the meantime. Are you able to distinguish salt production pond and coastal aquaculture pond already?
No. This is something that we haven't looked. No.
Okay. So I don't think we have any other questions. I would like to thank you once again, Nicola, for your very interesting presentation and for being with us today. I would like to thank again all the participants. And of course, we will make available the recording of this webinar together with the slides tomorrow on our BlueBRIDGE website. And I think we can close this session today. Thank you very much, Nicolas.
Thank you very much, Paul. Bye-bye.
Bye-bye.